Hey, everybody. I'm going to go on mute here for a few minutes just to let a couple more people dial in and try and do something about my cat. All right. Thanks, everyone, for dialing in. I think I've accomplished about as much as I can in terms of getting the cat to go away. So we'll go ahead and get started. So first, I'll ask just if there are any other questions about the homework. So project one. I know I've gotten some emails. I've answered some questions on the Discord chat, but I did want to just open it up. If there are any questions about it, or if anyone's kind of hung up on anything. All right. Well, then I take it that means everyone's good, and we can go ahead and start with the next sort of topic under our first unit. So this is the last thing we're going to talk about, kind of in the foundational topics of digital images and displays, and now we're going to do filtering and edge detection, and then after that, we're going to get into a lot more application-based stuff and a lot less kind of theory space. So what I'm going to do is I'm just going to go ahead and share my screen. Situated over here. All right. So we're going to, yeah, let's go up here. All right. So today we're talking about filters. It's kind of, our review so far. We've, talked about what an image is and formats. And last couple of classes, we talked a lot about coordinate shifts and coordinate transforms and how the format of a digital image is basically a coordinate system in which the pixels live. So there's, the RGB coordinate space, or there's a binary coordinate space that's just 0 and 1, right? Or, we've got kind of our between 0 and 1. However it works out, there's essentially the information in the pixel is a point in a coordinate space that's defined by the format of the image. And so, kind of based off that, we talked about the main three color spaces we're going to work in and the main transforms between them. So we were talking about hue saturation value, hue saturation lightness, and hue saturation intensity. We kind of looked at the Munsell color solid a couple times to see, hue is basically the color, saturation is the amount of that color present, and then value is the brightest color, lightness is the relatively brightest color to the rest of the colors inside the pixel, and then intensity is just the sum of all of the intensity in the pixel. So it's three different ways of measuring kind of the overall energy of a pixel. If you can think of hue and saturation as sort of what it looks like, value, lightness, intensity, that's kind of, how bright it is, or just an overall measure of how much energy is in that pixel, if we were thinking of it like a detector collecting photons to make colors. So we talked about those. We talked about moving between them and how we do that. I showed some examples on the notebook. That's pushed to the Git, and talked through some stuff. And we got our project 1, which is due Tuesday, that covers everything up through color spaces. So what we're starting now is, like I said, the last bits of this first unit are going to be filters and edge detection. So we mentioned this briefly last time. I talked about how, if we are trying to segment an image or classify things within an image, or, if we are kind of looking at an image and trying to move through it as if it were, an eyeball seamless classroom, the idea is geometry sort of matters more in computer vision than color. That's not always the case, but most of the time, you're going to start by doing some sort of filter and segmentation, which is going to involve some sort of edge detection. Right. We sort of thought through this in terms of if I need to, walk through a room, or I need to walk from the door to a seat, I can do that without needing to know the color or the texture of any of the objects in the room I'm trying to move around. I just need to know their geometry. So that's kind of why we start with edge detection, when everything is sort of built upon that, is because what we want to do when we first get a hold of an image to do computer vision is break it down into sort of its geometric primitives. And it's a lot like, I don't know, if any of y'all do a lot of like drawing or sketching or anything, or painting, or pretty much any kind of like art where you're trying to recreate something. You usually start from the base shape. So if you see, the posable mannequin dummies people use for figure drawing, right? It's not a person, it's a bunch of sort of representative shapes, circles and ovals, more or less, with kind of your occasional flat plane or rectangle, depending on the model. But the point is, sort of vision and computer vision, as a direct consequence, are largely dependent on geometric primitives. And so whatever computer vision you're hoping to accomplish, you need to start from, how do I get at the underlying geometry, and then how do I pick out the things within that, sort of geometric space, like we see here with the edges of the classroom. How do I then use that to find other things I care about? And at that point, it would be, I have the geometric bounding box of the chair. So now, if I want to know what color they are, I know where to go look within the image because I've sort of segmented out the seat of the chair using edge detection. And the most common place people used to start, and some classes still do start with, but it was the idea of this iris data set, which is one of, kind of the foundational data sets that's used in computer vision. And it was what I was working with when machine learning was still called fuzzy logic and computational intelligence. It was essentially the same thing. The idea was you learned features to make decisions. And this was sort of the data set we were given. So like in grad school, I had to write particles form optimization algorithm for detecting irises. So that was what we used it a lot for, was learning optimization techniques. Like you could do that, and you could do, a genetic algorithm. And those have really sort of fallen by the wayside as machine learning models have taken over. But that's, that is what we sort of learned to do with it when I was in graduate school. And undergrad was, learning how to optimize some algorithm for figuring out what is and isn't an iris and what species of iris it is. And so that's why you can kind of think of it like the traveling salesman problem. One of the very first problems you look at in computer science is the traveling salesman problem, and all sort of the computational burden associated with it, and then all the ways you try to avoid some of that computational burden. Different sort of heuristics you can apply to not get a perfect solution, but try to get a solution that doesn't take 100 years to run. And it's kind of the same way here, where you want to be able to create some sort of CV algorithm that can find a flower, decide if it's an iris, and then tell you what species of iris it is. And so that was, kind of the workflow, if you can think of, object detection and classification. What it is, we're going to want to take the image, and first thing is do some detection and decide if it's actually an iris or not. Like, is this, the right kind of flower to work with? And so then we, do some segmentation to break the iris down into, like I said, it's kind of geometric components. So like stem, number of petals, all these types of things. And then once, I've kind of found all of that, then I can do a classification. And so you can think, detection and segmentation start with a filter and an edge detector to determine, the basic shapes making up the flower. So I get those physical characteristics, and then to do my classification, I can go in and look at, well, what color is it, right? What pattern is on the petal? Are there stripes? What's the overall shape? So the idea is kind of to stress the importance of this is, looking at it in terms of how you find the features, how you then segment them out, and then how you do classification with those features. So it kind of covers all the steps of a good computer vision, project, pipeline, task, whatever. And like it says on the slide, this is a very long-standing problem. So lots of people have solved it lots of different ways. There was a time when like 50% of the repos in MATLAB code specifically were just looking at the iris data set for the type of stuff I was doing. And now obviously, you don't want to do machine learning with MATLAB because MATLAB has a really high computational overhead. It's not particularly optimized. And when I got the link here, so if you go right here, it is. You can find it in a lot of different places. It's typically hosted on, I forget who, but some schools, kind of ML department now holds it. But the idea is, it's the Fisher's iris data set. And the thing is, it was a paper from the 30s, 36, where, oh yeah, there it is, UCI Machine Learning Repository. I knew it was in there somewhere. But the point is, in 1930s, this guy went out and just measured a bunch of stuff about a bunch of different irises. And you can go through here and you can see all the pictures. There are tons of them. People have added on to this over the years. So there are, basically an ever increasing number of images you can work with. And if you look at the code, you've got some people put some code up. Some of this is, a year ago. Some of it's a few days ago, right? Which just goes to show a lot of people are still working with this. But let's see if it goes, I don't know if it lists them here. You can find it within the site somewhere, but Fisher basically took 6 characteristics. So, it was one about pistil height, a couple about petals, some about stem information. But he essentially distilled everything that he needed to classify an iris into these 6 values. And what people have done is use those values and those images to train models to figure out what kind of iris it is. So that's, kind of a lengthy explanation of, where this data set comes from and why it's so popular. And you'll probably hear about it a lot, though a little bit less so now. But it's still a really great place to start for doing some cool computer vision stuff and now some cool machine learning stuff. So what we're going to do now is look at some of these images. We're going to look at a few of the iris images and kind of use those to highlight why we need filters or why, we do the kind of pre-processing we do on images. So everything we've done until now, you can think of as kind of like formatting the image, right? Everything through kind of loading it in and then doing some sort of transform to a different coordinate space or color space. All of that is getting to sort of the image itself ready for processing, right? To where you've got it in the space you want, in the format you want. This next step, filtering, is sort of like the pre-processing step. So, if we look here, and I just run an edge detector on these pictures. So these are 3 pictures of, an iris from the data set. And on the right is all of the images, all of the edges in that image. And so if you come back up here, right, I can just run a Caney edge detector, which we'll learn about next time, but I can just run an edge detector that I got from OpenCV. And I get back, desks, chairs, and a window. So it works okay here. When I try to just take it out of the packaging, essentially, and run it on these iris pictures, I kind of just get back garbage, right? Because with a basic edge detector on an unprocessed or unfiltered image, kind of like we talked about, it looks for big jumps in values. And because these images are noisy and have a lot of, grass in the background and a lot of brighter parts and a lot of dimmer parts, it just essentially picks out an amount of edges that is functionally useless. Right. There's really nothing I can do with these images once I've picked the filters out because it's just too messy and there are no real distinctive features. So that sort of brings us into this idea of image pre-processing and looking at filters and then why we need them. So like we've kind of talked about so far in the semester, different CV algorithms need to see different parts of an image or different attributes, right? We can't really do good edge detection on an RGB image, but we can do good edge detection on an HSI image, right? Or conversely, if I'm doing some sort of color selection, then I can do that much easier in an HSL color space. And so we have these different color spaces because each one sort of brings out features that make those features easier to detect and segment. Because, here I can run it and I get everything back. So what I need to do is find some sort of filter that will, make these images look more like this edge detector, right? I just want the biggest, strongest, nicest, crispest edges. And to do that, I need to filter it so that I can present the image to the edge detector in a way it likes to see it and it can think a lot better about what it's looking for. And so that's why we're talking about pre-processing and filters. And we're starting where we are with edge detection, which is just geometry. It doesn't really care about anything else. And then once you get into segmentation and classification, you can then go back and take the colors from the things you've segmented, from the geometries you've found, and use that to understand more about what that particular feature of the image is. And so when we come at this from a filtering perspective, because images work like a function where each location in the image is determined by some function, and because physically, if we think about creating an image, we're just collecting photons. And so that lets us use signal processing stuff to filter our images. And that, kind of helps out and makes things easier for us because there's already a boatload of stuff from the signal processing world that we can just, kind of be a little clever about and apply in our space versus, just a regular signal processing space. So for pre-processing, there are in general, two kinds of image filters or two ways of pre-processing an image. One of them is filtering, which is where you directly change the values of a pixel without moving it to another place. So we can filter whatever the pixels are, whatever information the pixels contain. But when we do that, we can't move them because filters, use averaging functions that require everything to be essentially where you want it to be or where it's supposed to be. And warping is the opposite, where you are changing a pixel's location without changing its value. So I can either filter what's inside the pixel or I can move the pixel. I might ultimately want to do both, but I can't do them at the same time. There's no filter that can warp an image, and there's no image warping algorithm that filters an image at the same time. You have to do one, then the other. And if you're going to warp, then filter, it's going to change a lot of things because you're averaging spots you wouldn't be if you hadn't warped it. And, if you filter a warped image and so on. So the main thing is we do both. We will do both. They're both pretty great for trying to do computer vision. It's just important to remember that you can change what's in a pixel or you can change where a pixel is, but you can't do both simultaneously. You have to decide if you want to warp and then do some sort of filter, or filter it and then do some sort of warping. So that brings us to digital filters, kind of the main thing we're talking about today and Tuesday. There are a lot of different kinds. We're going to be looking at segmenting and smoothing and sharpening and blurring. Those are some of the big ones. There are lots of ways to filter images out there. But in general, what we're going to do in this class and how it all sort of works at a 10,000 foot level is, you're going to either smooth out everything in the image sharpen everything in the image, blur some parts of the image, and then go in and try and segment out what you want after you do that stuff, with the goal being making the segmentation easier by presenting the image in a format that that algorithm wants. And for these, so the filters we're going to cover are changing pixel values, not locations. So these are all filters. We're not talking about any image warping yet. We're just talking about filtering the pixels inside the image. And like I said, that's sort of, these filters are kind of your pre-processing tool to get ready for the actual, computer vision part of computer vision. Your goal is to, get the image you want and then turn it into an image the computer wants to then do the algorithm. And so that's the idea. And we're going to cover first the high pass and low pass filters. So high pass and low pass filters are essentially exactly what they sound like. If I'm doing a high pass filter in some sort of traditional signal processing, what that ultimately means is I'm just throwing away every point below my threshold. So if it's, sound, I would throw out, all the sounds below a certain level and only have really loud stuff left, so on and so forth. But it is exactly what it sounds like, is it's a filter that's only going to let some percentage of the most intense data through the filter. So signal processing, we're killing things below a certain frequency. In light, frequency is just another measure of energy. Higher frequency is more energetic, right? That's why UV light is bad for you and IR light isn't, because as wavelength decreases, energy increases. So frequency is our measure of energy for light. And so in images, that is sort of a direct corollary to value of lightness and intensity. And that is why, we spend so long talking about those color spaces, is because hue saturation spaces with either value of lightness or intensity are the easiest to filter with a high pass or low pass filter, or even a blurring filter, because your goal is to get rid of low energy stuff with a high pass filter, or get rid of high energy stuff with a low pass filter. And in both cases, it's filtering whatever you are measuring sort of intensity in, be it value of lightness or intensity. It's going to pass pixels one way or the other based off of those values, which is why we use them, because it, lets us just use this filter kind of as is. And it's ends up working out really great. So high pass and low pass both operate in some sort of hue saturation space. And they operate the same way, but they have the same sort of mathematical model behind them, I guess is a better way to put it. But the math you use for it is different. And it works a lot like HSV, L, and I, where one is a value of the most energy, which is like a high pass filter, which is essentially just looking at the things with the most energy. There are filters that sort of look at, the relative intensity of a pixel. So that's like, looking at the average, the relative lightness. And there are ones that just care about total energy, which is like intensity. So in the same way, those spaces break it apart in terms of how they measure the energy. Filters are kind of broken apart in terms of what they do with that energy to find a filtered result. And, it's kind of the same three options, right? We've got brightness, relative brightness, and average. And that's how our filters are going to work similarly. So we'll start with high pass filters, and the way they work is they use a convolution matrix, or you will almost always see it called a kernel. So both high pass and low pass filters use convolutional kernels. And it is a sliding window that slides through the entire image and determines a value for each pixel based off of its neighboring pixels. And then you come up with that value with your sliding window by computing the pixel based on its neighbors. And that value is either passed through because it's above your threshold, or it's, thrown out because it's below your threshold. So essentially, doing this is we're only looking at one dimension of the pixel, which is its intensity or its brightness or its value. We're looking at that. We're comparing it to all his buddies who live next door to him, so all the neighbors. We multiply all that out and we sum it up, and we're left with one value for that pixel for its value, lightness, intensity, and then the thresholding is applied to that pixel. So if we assume we're doing a 3x3 convolutional kernel for a high pass filter, what we do is we take our matrix and we lay it on top of each pixel, and we multiply the pixel values inside the matrix by the values of the matrix, add them all up, and that is our new pixel value. So this is, for a high pass, like I said, this is sort of computing the maximum amount of energy a pixel has, as a function of everybody around it. And then it just looks at that max energy and, again, throws a threshold at it. So, and again, so like I said on the last slide, we're going to see, as we do examples and everything, it defaults to a 3x3 kernel. It does not have to be 3x3. It can really be any size you want. It just sort of depends on how long you can take to process something, how long you can let the filter run, because a bigger kernel means it runs slower, or if you just want a bigger kernel, and we'll see how that kind of changes things. But the idea is, if I start from my checkerboard, just binary 3x3 image, so I've got my array, it's just the identity matrix. And my images, I've got these three blocks running down. So if I set my convolutional kernel, which is also 3x3, as 222, what happens is you go in and let's see. So if you sort of think of this as, so if I think of the, so if this is my convolutional kernel and I've laid it on my image, then what I have is, I really wish there was some form of board you could use for something like this. But so you've got your two here, two here, two here. So every pixel in the window is multiplied by whatever number is here. So the only one in this range is a 2. So my output image is going to have a 2. So if we look at this as the output image, so this is a 2. And then what you do is move the box over another step multiply everything and sum it up. So if I was in this point, say, then I would have this kernel overlaying it, which is, 2 and a 2 and a 2. And that would be multiplying 1 by 2, 1 by 2, 1 by 2, and sum it all up. Then, my center pixel here is going to be a 6. And it kind of step throughs like that. It's hard to draw without a blackboard, like I said. But you just think of it as a sliding window where all of the pixels it overlaps, multiply the kernel by the value. So you just do a bunch of multiplication. And then for the high pass, you just add everything up in the kernel and put it at that point. So this would also be a 2 because now your kernel is kind of poking out like this. And so on, gumball. So that's the high pass filter. We're just moving a convolutional kernel across the image, multiplying a bunch of stuff, and then summing a bunch of stuff up. And what's going to be left over is only the brightest points. So, the higher the sum is, the more points I'll keep. And you can think of it in a couple of different ways. If you, have a convolutional kernel with very large values, and you'll get much brighter stuff, and that'll kind of affect where you want to put your threshold, etc. So a low pass filter is usually, you'll see it called a box filter most of the time, because there are a lot of different kinds of low pass filters. High pass filters are, really simple, and they don't get much more complicated than just a multiplication and summation. Low pass filters come in a lot of different forms. And so you'll usually see them by kind of their name, because there's Gaussian filters and there's log filters, which is Laplacian of Gaussian, and there's box filters and mean filters and averaging filters. All of that stuff falls under this idea of a low pass filter. And where the high pass filter is doing all of these multiplications and then summing them, a low pass filter is doing all of these multiplications and then averaging the sum. So that's kind of why it's called often, it's an averaging filter or a mean filter, or you'll hear called a blurring filter as well. And it's because it averages things out. So with a high pass filter, you're basically going after the most intense pixels and only keeping those. And then with a low pass filter, you're kind of smudging everything into, an average, and then keeping stuff below some sort of threshold for your average. So again, it's usually a 3x3 matrix. The convolutional kernel is typically 3x3. Again, there's no actual constraint on size. It just 3x3 is kind of optimal, and it's what OpenCV really defaults to. And, traditionally that's just the size people use. And depending on your application, if you want to get super fancy or do any neat stuff, you can use different kernels. It doesn't have to be n by n. You can have sort of a 3x2 or a 4x1 or whatever. You can have the kernel be whatever you want. The operation is the same, where you're just sliding it over each pixel, doing a multiplication, and then either an addition or an addition and average. But you have options. So this is, like I said, you'll see it called box filter. Most of the time, that's kind of the most common way to think of it, because it's a box. They're sliding windows. But the point is, you've got this convolutional kernel that's got some dimension, usually 3x3. And for the low pass, like I said, or this box filter, is we multiply and add everything and then take the average, versus the high pass where we just multiply and add everything. And so, if you can look at this, you've got kind of a similar state. And if you think of, I've got my image here, that's all ones. And if I lay this kernel on it, then what I've got is, a one here and a one here and a one here. But I multiply this all out and I have one. And so my output image now has, 1/3 in this corner because I averaged it instead of summing it. So this would be 1/3. If you look at the middle, when I'm in the middle pixel, it's, ones times one. So I get back just a one. Over here is like 1/3 again, and so on. So if you think, with the high pass filter, I end up with, more intensity, a higher value. So it's, 262. Here it would be 1/3, 1/3. So because it's a 3x3 and I'm just doing an identity matrix, I'm essentially cutting everything into 1/3 of its original value if, we use this kind of kernel. So that's just to kind of show the core concept of, we're taking this convolutional kernel, we're sliding it across every pixel, and then we're doing, again, multiplication and then adding and then an average or a max. So the most common approach to low pass filtering is to do what's called a Gaussian blur. The only difference between a just generic low pass filter and a Gaussian filter or Gaussian blur is that it's a weighted average. So you're kind of giving more value or more importance to certain places within the image or certain spots within the convolutional kernel. So it's basically just a low pass filter with a weighted average. It's called Gaussian for some stuff we'll learn about a little later on. But the main thing is, it's a weighted average. So you've got your high pass, which is just the max. You've got your low pass, which is the average. And you've got your Gaussian, which is your weighted average. Right. So all of them default to a 3x3 kernel. High pass is, we want the highest intensity. Low pass, we look at the average intensity, and Gaussian, we look like the relative intensity. And that's why I kind of said it's similar to, value, lightness, and intensity, where, one is just the max, one is the relative max, and one is the average. And it's the same way for these filters. One's the max, one's the average, one's a weighted average or a relative max. And so we're going to go through a demo now and then come back to this and kind of explain what we're seeing. So we're going to, start with our filters, right? And before we do any filtering, we just want to look at what does this look like. So you can see edges. I've just used the CB2Caney function. Those are the default parameters. That's what you should use for project one, just what it comes with. Don't mess with any of that stuff yet. And we're giving, basically default what it comes with. It's a 3x3 kernel. We've got these 100, 200 that we'll learn about later. And, what we get is this really nice image where we have really clear edges detected. It's not too noisy. We can definitely get what we want to get without having to really filter it first. If we look at an image that is a little more complicated, where we've got, our image of the tiger statue chilling out in front of whatever cool space age building that is. I've never actually been to Rochester, though the closest I got, I believe, was Rome or Utica, which on another tangent, people thought Utica was kind of scary, and I guess New York sketchy neighborhoods aren't quite the same because no one tried to shoot me at a gas station, and that's not terribly uncommon in the Deep South. So anyway, that's where I've been. It seemed nice. I've never been to Rochester. Um, so I've never seen this cool tiger statue, but it looks cool. But, all that to say, if you look at it, it's a lot more complicated. And because I'm just going after everything all at once, again, I get stuck with every edge, right? Anything that looks like a line, anything that looks like an edge, anywhere there's a change in color, it's going to flag because, without filtering, it doesn't know what to care about. So it kind of defaults to caring about everything and gives us back a pretty messy image, though it's still clear that there is a foreground and background and that the statue is in the foreground. So, what I want to do now is we're going to look at some iris images. So, I had a slide of these. It showed they don't look great, right? In this instance, again, it doesn't know what to care about. So it picks every edge. And in these images, they're more complicated than, our tiger is still obviously a tiger and a building, but when I get to this level of complexity, I can't tell anything from those images, from the detected edges. I can't pick out any sort of features. I can't really find any sort of foreground or background. So if I try to do edge detection the same way I did with a room full of desks, as I do with, irises or some other, equally complicated image, it does not work. And the reason it doesn't work is because we needed to filter it so that the edge detector would have an easy time finding the things we want it to find. That's kind of the point of the pre-processing. And so what we're going to do next is we're going to do, a high pass filter and a low pass filter and see what these images look like. And like I said on the slides, you will almost always see a low pass filter called a Gaussian filter or a Gaussian blur, so much so that that is what it is called in OpenCV, is a Gaussian blur. And the reason to kind of talk about the low pass filter side of it is both to, show that it's still a convolutional kernel, but also, explain that the Gaussian is a weighted average, and there are ways to do a non-Gaussian low-pass filter in Python, but it usually means creating kind of your own kernel and walking through it, just because Gaussian is sort of the default. And if you, set everything to like a third, if it's a 3x3 blur, then, or a 3, you can kind of get to a normal average if you just set all the weights the same. So what we want to do is we want to look at these 3 irises, and then we want to look at them with a Caney edge detector, and a low pass filter and a high pass filter, and detect edges and see what works best. So we start here, and this is just showing the filtered images. So we're not looking at any of the edge detection yet. We just want to see what the filters look like. So we've got, our original image, our high pass filter makes it, way more prominent that there's a flower there. And our low pass filter just kind of looks like a somewhat blurry black and white version of the original image. So we've got that, and our next 2 images kind of the same. The original image, the high pass filtered looks, a lot better to me as a person. The edges are way more pronounced than in the low pass. You can see in the bottom one, I've got, essentially a very pronounced flower in my high pass filtered image and just sort of a blurry or image in my low pass filter or Gaussian blur. So if I want to take those and find the edges in the high pass and low pass filtered images, it turns out I get the opposite result from what you might expect. Because for us as people, when we look at these high pass filtered images, yeah, so we see these lines really well when we throw away all of the low frequency information, the low energy stuff. We end up with what to us looks like, a very prominent flower, very easy to pick out compared to the low pass filtered image. But it turns out that edge detection on the high pass filtered image is still terrible, right? And the edge detection of the low pass filtered image looks a lot better, right? So the question is, why does a high pass filtered image that looks like a flower, come back with a bunch of garbage, and a low pass filtered image, which just looks like a dim, blurry version of the image I had to begin with, looks way, way better. So it's counterintuitive, and it kind of, shows the difference between people seeing things and computers seeing things, and moving through different color spaces that make more sense to a computer. Because, a person is going to want to use this to try and find the flower, and a computer is going to want to use this, and it's, a function of how a computer reads an image versus how a person does. And because of the way it works, it turns out low pass filtered images are much, much, much better for edge detection than high pass filtered images or unfiltered images. So we're going to go through all of this Tuesday. Like, we're going to kind of get into the actual edge detection algorithm, which is also a convolutional kernel, just a much smarter one than a 3x3 or m by n that you just do a multiplication and then a sum. They're a much more sophisticated convolutional kernel. It's called a Sobel operator, and we're going to talk about that to death starting on Tuesday. But this is just to sort of set the stage for discussing edge detection, in the sense of, we need to pre-process it, and we need to pre-process it in a way that the computer likes instead of a way that a person likes. And so that's kind of setting the stage. And then I've just got, some code in here that'll show how we can play around with the convolutional kernel. So, over here, I've got, a kernel of all ones we looked at, or if it was just all twos, we can kind of mess around with that a lot of different ways by just defining the kernel. And so, what you do is, my kernel is this 3x3 matrix, and now I'm using a filter 2D function and a high pass kernel. So I'm basically just saying, do a box filter with this kernel, and take the values that are above my threshold. So I'm building kind of a custom high pass filter by looking at some different convolutional kernels. And here's 2 and 8. Here's where I'm only keeping the middle one, and we can kind of look at the results here. And so kind of our initial one looks pretty good, at least to us, right? It looks like, these images. So it's kind of brought out all the edges for a person. right? And you can see from this, it's all minus ones and an eight. So because it's summing every pixel within the kernel, right, it does a multiplication, adds them together. Essentially, it's whatever the pixel I'm looking at, I've multiplied by eight, and then I'm just subtracting the values of everything around it, which is why you see, these lines get thin, is because for each, pixel, I'm essentially making that pixel way brighter, minus all the pixels that are around it. So if all the pixels around it are really high, it doesn't matter that I've, made it 8 times brighter. The summation is going to come back pretty dim. Whereas if I use negative values in the kernel, then it's just going to make, the bright stuff pop a lot. Conversely, I can do this where, I've got all twos and an eight. So now I'm, making everything much, much brighter. And, my filtered image kind of cuts out like this. And this last one was just a one in the middle. So because it is multiplying everything and summing them, if I have a convolutional kernel that's just a one in the middle, I get back exactly what I put in, right? It's just multiplying everything around the pixel by zero and the pixel itself by one, and then adding all that up, and I'm, right back to where I started. Whereas, kind of with the default where I was doing, I want to make the pixel brighter and subtract out everything around it. I get this. So that's to just show, how you can create your own kernel, and what, how it kind of works based off of the values you choose, where, I can either get back something that looks like this with one kernel or something that works like this for another. And the idea behind that is to show, in OpenCV, you have a lot of default options. But if you don't understand how a convolutional kernel works for the filter, you could get back, any of these filtered images, depending on how the kernel is predefined, and then, not have a deeper understanding of why it looks the way it does. Kernel parameters are, like a lot of things we've talked about so far, is just another one of the things, people who don't do a lot of computer vision can just go in and change arbitrarily and see a huge change in the output. The difference in a high pass filter between these first two kernel parameters is huge. And it's huge because in one case, I'm making part of it bright and then making it dimmer based off of the brightness of everything around it. And one of them, I'm just making it super, super bright. So I'm projecting everything way into the white space range by, kind of maxing out intensity everywhere. And if, I just do this, then I'm back to my original image. So when you are working on things sort of out in the wild, it will serve you better if you know how the kernel works and how the filter works, so that then you can go in and do something like create a custom kernel that you understand what it is doing and how it is filtering, and you know why you get the results you get. And then if, you want some variation of this, you can kind of go in and do that. And it's the same thing with the low pass filter. I can start with, as you change the kernel values for the low pass, you either blur everything, or you blur it a little bit, or you blur nothing. Um, I think this is not the code that does that, though. So this is, right, so this is just blur, which is just the simplest form of a low pass filter, like I said. So you can think, a CV2 blur is kind of your default for a low pass, whereas if you look at uh, filter 2D, that's kind of where you start for a high pass filter. So you're going to use some, variation of the 2D filter in OpenCV to create a high pass filter where you can go in and make your own kernel. For low pass filtering, you start from this blur idea. So blur is just kind of how it defaults to a low pass filter, and Gaussian blur is kind of the that's what I'm looking for. Weighted average is the Gaussian blur. Normal average is blur. So this is sort of the base layer of your low pass filtering. Can kind of filter it down, and you see the more you blur the image, you kind of get nothing, and then you kind of get what you want, and then you get back what you put in it. And then here is a demo for Gaussian blur. So in this case, we're using a weighted average for filtering. And what you can see is as I change values, the stuff inside there gets blurrier, right? So with just low pass, what's happening is it averages everything in the area. So when you start at the top, right, it's averaging across, this RIT, which are very big, pronounced black pixels. And as the box moves down, right, you've got sort of decreasing amounts of black until you get to the bottom where it's just sort of averaged everything out to white. And if you, do it with a better kind of averaging idea, then you can get less blurry and then no blurry. When you do it with a Gaussian blur, because this is a weighted average, what happens is instead of averaging everything kind of through here into black, it weights the averages to where it's looking more at the central pixel and less at averaging every pixel. And you get more of what you would really think of when you think about Gaussian blur, or when you think about blurring in general or smoothing, right? The point is, the difference is, if you do just a low pass filter, you can get, just a blurred out everything. If you use a Gaussian blur, so you use a weighted average, then you get kind of what you want, which is just a really blurry version of what's already in the image. The one thing about Gaussian blur is in OpenCV, it's really hard to get into the weights to change them for a Gaussian blur. So this is why we have to come in and sort of define our own kernel and then use the filter 2D with our custom kernel. So Gaussian blur kind of comes with a lot of defaults in OpenCV. So more often, a lot of what we do, you can just use what's out of the box. But if you are getting a little more clever, right, or you want to do something, special for your application, then you can create a custom kernel and run that in the filter 2D to essentially make your own kind of Gaussian blur. And when we do that, we come out with these images. So you can look through this. It's about time, so we'll probably start wrapping up. But again, this notebook is out there. You can look through this, and if you kind of look over the code, you can see the changes I'm making to the kernels and the filters to get these different results. And that just sort of helps show, how the kernel works, what values go in the kernel. and how, by knowing what the math under it is, right, what that matrix is doing, towards the edge up here. Oh, why is it like black at the top and then slowly goes down to white? Um,
Excuse me, Professor, can you hear me?
yeah, yeah.
Yeah. Oh, okay. Yeah. No, yeah. Sorry, my mic wasn't working well
Oh,
the
okay.
last few days, so I just thought I'd type it in. I'm just kind of curious at why it's most concentrated towards like the top left as opposed to the whole of
Yeah,
the top of the image, because the RIT, like, it seems to be pretty evenly spread, like the amount of black, but then when we look at the filter, it seems to be highly concentrated only towards the corners. So I'm a bit confused about that.
yeah. Give me 1 second. I know there's a reason, but I forget. I'm going to make a note. I know there's a reason for it, and I know why. I just can't remember what I know about it. Um, so, yeah, I'll drop that in the Discord after I figure it out because I
Okay.
totally
All
already
right.
know, right?
Yeah.
Yeah, I
Yeah.
forget, but I will look it up and put it in the Discord once class is done. We can look over this again.
Okay. All right. Thank you, Professor.
Nope. Okay. Um, so with that, we kind of get to, our last slide, and this idea going into next time when we start doing edge detection is, when do we use high pass and when do we use low pass and when do we use Gaussian for edge detection? So the high pass filter, we can say kind of looks edgier. So we see the flower. But the question is, why does a low pass filter make for better edge detection? So, like I said, and what we're going to talk about, the canny edge detector looks for big jumps in intensity. So it's looking for places where things are changing very quickly. Uh, and it uses the gradient of the image to find those jumps. So if I'm looking at, how much the change is changing over time, which is essentially what a gradient is for, um, then they're going to be less big jumps in intensity. And what that does is, rather than as we think of it, if we make the jumps in intensity lower, it'll be harder to find edges. What that ultimately does is weeds out a lot more of these smaller jumps or kind of cuts down on all of the places it thinks is changing fast enough to be an edge. And so that's kind of how it works, is this idea of we want to go from, lots of areas with lots of small jumps inside them or lots of small areas with big jumps in them. If we blur that out, then we get kind of one small jump in a big area. And, thresholding kind of determines that. But what I mean by that is if we pull this back up, you know, in our high pass filtered image, it's looking for big changes in intensity. And so it sees all of those big changes, right? Everything sort of jumps out as an edge. If I blur everything out and I make it smoother, what that does is it's going to find more large edges and less small edges. Because when I blur it, if you think, even in just kind of this top left corner where you've got, this grass and this grass, behind this, you have all these little lines, right, that all stand out as edges that stand out here. When I blur it, those kind of get blurred out to where it only sees, the big, large lines. So blurring makes all of the little changes kind of go away, whereas a high pass filter makes all of those little edges pop out. And next time when we go through it, we'll go over the Sobel operator and how that does edge detection and how it uses a gradient versus just a change. It's a change of the change essentially. And I'll figure this out because I know why, and I have it in some notes somewhere that will help it make sense. So that's where I'm going to stop for today. I put a really cool paper on the My Courses. It's about reverse image filtering. That is, conceptually pretty interesting, where the idea is, can you undo the effects of a filter by using that filter kind of on itself, right? So it's like, can I use a filter to undo what that filter did? So, trying to go back from the blurry gray image to the sharp, colorful image. So that's pretty interesting. The AI tutorials are super cool. And then, there's just a short video on there that kind of talks through all of this again, much more succinctly. So, yeah, with that, I'll wrap things up. I guess if anyone has any questions or needs anything about the homework, go ahead and shoot me a message or drop it in the Discord. And y'all have a great weekend, and I'll see everyone Tuesday. All right. Bye.